Hey guys, welcome back. Today we're going to solve LRU Cache, problem number 146 on Leetcode. So the problem statement says to design a data structure that follows the constraints of a least recently used cache. First, we'll talk about what an LRU cache is, and then we'll jump into the code. Okay, let's get started. A great way to visualize an LRU cache is to imagine visiting websites on your computer. Before we've visited any websites, our cache is empty. So first we visit website A. Our browser then caches website A and stores it into memory. Next, we visit website B. This time, when we store B in memory, we move A over to the end of the list to indicate that it was the least recently accessed website. Next, we visit website C. When we try to store C into memory, we see that our cache is full. So we go to the end of the list to the least recently accessed website, and we remove it. Now we can shift B over and add C into the cache. Now let's say that we revisit website B. So first we check, is B in the cache? We search through the cache, we find B, and we return what we need to render the website quickly. However, in the worst case scenario, that website is at the very end of the cache. We have to search through every single value in the cache to find it. And the problem asks us to find a solution where adding and retrieving values from the cache happens in constant time. So what we can do to achieve that is maintain the locations of each of those websites in our cache. Using this method, we can very efficiently query our cache and ask it, does B exist in the cache? And it does. And here's exactly where to go in this data structure to find it. So this is kind of a hint as to what kinds of data structures we'll need in order to achieve that O of 1 time complexity. We'll need a linked list where we can keep track of what's been most recently accessed and what's been least recently accessed. And we'll maintain a hash table, which will tell us exactly where to go in the linked list to find the website. If you're not already familiar with how linked lists and hash tables work, go check out my videos in the description box below where I explain exactly how they work and how to implement them in Python. Okay, I think we're ready to jump in and start coding. Let's start by defining our LRU cache class. We'll initialize it with a set capacity, and we'll use the dictionary class to initialize our hash map. Next, we'll create our linked list. So we'll start with the head and our tail. We'll go ahead and connect the two by setting head.next to our tail and tail.previous to our head. So we're essentially creating a doubly linked list. Having a doubly linked list means we can travel across the list in both directions. We don't just have to start at the head. We can be given a location within the list and move either towards the head or the tail. I also just want to point out we're not initializing the head and the tail to none to start. We're using these dummy nodes as placeholders. It gets a little complicated if you don't do it this way, so I do highly recommend having a dummy node on either end of a doubly linked list. All right, so moving on to our node class, it looks pretty standard. It'll take in a key value pair and we'll initialize the previous and next nodes to none. So first, let's write a method that will retrieve a value from our cache. Our get method takes in a key. If it doesn't exist in our cache, we should go ahead and return -1. Otherwise, let's go into the cache at that key and retrieve the node that we've stored there. So at the end of this method, we know that we can return the value of the node. We also need to change the position of the node within the linked list to indicate that it's now the most recently accessed node. The easiest way to do that in a linked list is to first remove the node from the list and then add it back in at the head. Let's define some helper functions to execute this logic. So we'll need a remove helper function and an add helper function. Let's start with defining the remove function. So to remove a node from a linked list, we need to set the previous node's next value equal to our current node's next value. We do the same process by setting the next node's previous value equal to our current node's previous value. Let's define our function that will add a node to the beginning of the list. We'll keep our dummy node at the head, so we'll essentially insert our node between the head and the head's next value. We'll start by storing the value of head.next. Then we'll link our current node by setting its previous value to the head and its next value to head next. Now we can rewrite head.next to our node, and we can set head next's previous value to our node. Now let's define a function that will put a new value into our cache. If this key is already in our cache, we'll need to go ahead and remove it so that we can insert it at the most recently accessed position in our linked list. Next, we'll create our node and we'll add it to our linked list. and we'll save the location of our node in our cache. We also want to account for an edge case where our cache exceeds our capacity. So if that's the case, we'll have to remove the last item in our linked list. And we'll define that logic in a function that we'll call remove from tail. This is a pretty straightforward method. We'll take the value at the end of our list, so the value that's right before the dummy node at the tail, and we'll call our remove helper function, and then we'll delete that value from our cache. The last thing I'm going to do is drop in this helper function that will print out our linked list. So let's check that everything's working. We'll start by initializing a cache with a size of 2. And just like in our example before, we'll visit website A. And if we go ahead and print that out, we can see our linked list has those 2 dummy nodes on either side, and website A is the only value in our cache. Next, we visit website B, and now we see that website B is at the beginning of our cache. Finally, we visit website C, and website A has been removed from our cache because it's the least recently accessed site. When we visit website B, now we see that B and C switch places because B is the most recently accessed site. All right, now that we seem to have come up with a workable solution, let's go back to Leetcode and see how it performs. So it looks like the runtime of our solution beats about 75% of other Leetcode users. The memory could definitely be improved, so that's something we can work on in a later video. If you have a different solution or have ideas about how to improve our LRU cache, leave a comment below. And if you like this video, please give it a thumbs up and subscribe to the channel, and I'll be back next week with another Leetcode solution. Thanks so much for watching, and I'll see you next time.